I would like to thank the sponsor of this video, Brilliant. One of my earlier misconceptions was confusing chaos with randomness. Chaos and randomness are not the two faces of the same coin. These concepts are often used interchangeably, but they are fundamentally different. Randomness is purely arbitrary. It follows no rules, no set of equations at all. While chaos stems from the inherent unpredictability in systems, a result of even the slightest errors in the calculations or assumptions. Every chaotic event in this universe boils down to only one thing: the mathematical unpredictability. Chaos is pervasive, appearing everywhere, from the motion of a double pendulum to the dynamics of weather systems. It seems to be woven into the very fabric of the universe. This unpredictability arises from the two key characteristics of a chaotic system: sensitive to the initial conditions, which means a slight change in the initial conditions can drastically alter the future outcomes. And the second is the unpredictability. The limitations of the measurement accuracy or the computational precision make long term predictions nearly impossible. Both of these reasons are responsible for why doesn't any weather app forecast the weather for more than a week. It's not that the technology is not capable to predict for weeks or even for months. Even if it does, there's a high probability that the prediction is going to fail. The same technology can predict the eclipses, even the trajectory of comets, hundreds or even thousands of years ahead in future. If you're thinking about the dissimilarity between the two events can be the reason, then the prediction of the tides can be worked out months or sometimes years ahead. Why is that the weather forecasting is so challenging for scientists? You may have heard the phrase, the flap of a butterfly's wings in Brazil can set off a tornado in Texas. But is it really true? I mean, there are thousands of butterflies flapping their wings at any moment. If one flap could bring the tornado, wouldn't others do the same? The point I want to highlight is not the literal truth of the phrase, but its metaphorical and mathematical significance. As strange as it sounds, the phrase clearly signifies how a small change in a system can result into a completely different outcome. A butterfly's flap subtly alters the environment, and if that change is allowed to evolve in a simulation over time, the resulting outcome could diverge entirely from what would have happened without it. This sensitivity to initial conditions is a hallmark of chaotic systems. Of course, tides and weathers are two different systems, but both share a similar number of variables. Weather is chaotic and unpredictable, while the tides are predictable and governed by orderly forces. So, what introduces chaos into the nature? Why is there chaos in the universe? Attempting to understand chaos through something as complex as weather simulations is daunting. Let's explore the essence of chaos with a simpler system. This ideal pendulum is undamped, meaning its oscillations never fade. If I shift this pendulum to a certain angle and let it swing freely, the motion we can say is clearly periodic. To visualize this periodicity, we can plot its phase-space diagram, a graph of momentum versus position. In this diagram, the trajectory forms a closed ellipse, with the dot eventually returning to its starting point after completing one full oscillation. The shape and size of the ellipse are determined by the pendulum's initial angle. Basically, the elliptical trajectory represents the energy of the pendulum. A higher energy results in a larger ellipse, while a lower energy of the pendulum produces a smaller ellipse. But all of them will be concentric. This periodicity implies that once a point is on a trajectory, it will continue to follow that path. There is no mechanism for the point to deviate from its trajectory on its own. If I take two similar simple pendulums separated by some angle, their relationship remains fixed. One pendulum will always follow the other, maintaining a consistent relative position over time. Once I know the initial conditions, I can accurately predict their future motion. This predictability demonstrates that the simple pendulum is an ordered system. Now, let's consider a double pendulum, where the system involves four parameters: the lengths of the rods and their initial angles, theta 1 and theta 2. If I simulate two double pendulums separated by a small angle, let's say 0.01 degrees, and allow them to evolve, we can observe The relative position between them becomes completely unpredictable. Unlike the simple pendulum, these trajectories are entirely unrelated and defy any predictions we may make. This is the hallmark of a chaotic behavior. The chaos entered into the system implicitly. But how? Where does this chaos come from? And for that matter, what makes a system sensitive to the initial conditions? To explore this further, let's examine another system with only one parameter. And this fascinating system was introduced by Matt in this number file video. Imagine a particle wandering in a 2D world in some peculiar fashion. It starts by taking a step and then turns by a certain degree, let's say theta. Then it takes another step in the new direction and rotates again. But this time the angle is 2 theta. And with the third step, the rotation is 3 theta, and so on. You get the gist, right? And following this procedure, after the 4000 steps and with theta equals 1.02 degree, pattern emerges. Now observe what happens when theta is 1.03 degrees. The resulting output changes drastically. Despite its simplicity compared to the double pendulum, this system exhibits chaotic behavior. To better understand how chaos enters into the system, I'm gonna simulate this by increasing theta in increments as small as 1 millionth of a degree. Even such a tiny change in the input leads to a drastic difference in the output. However, upon closer inspection, not all points are affected equally. As you can see when I zoom in, points closer to the center experience significantly less change compared to those further out. This disproportionate on the outer points arises from the way the system is structured. The difference between the points lies in the number of degrees by which they are rotated. As the distance from the center increases, the rotational effect becomes more pronounced. The outer points are more rotated than the inner ones. For instance, the rotation of the particle at the nth step is n times larger than at the first step. So the output will be n times larger. So the net rotation of the particle at the nth step is formulated to be n plus 1 by 2 into theta. So clearly a slight change in theta will evolve as n square. The higher the value of n, the larger is the difference. You see, this nonlinear term, it is a root cause of the chaotic behavior we observe in the system or in any system. The farther we move from the center, the larger the difference becomes. It's a hidden evil of all the problems. It doesn't matter how many parameters the system has. The system will be chaotic if it exhibits non-linear behavior. And this nonlinearity is clearly visible in the equations governing the double pendulum. Chaos is fundamental. It emerges as a consequence of nonlinearity. How parameters interact with each other in such systems give birth to nonlinearity, and that in turn gives birth to chaos. To gain a deeper understanding of math concepts, I personally use Brilliant.org as a learning resource, and I would like to thank Brilliant for sponsoring this video. Brilliant is an interactive learning platform that helps you get smarter every day by building practical skills in areas like physics, problem solving, math, data science, and AI programming. What makes Brilliant apart is its hands-on approach to learning. Instead of passively consuming content, you will dive into the real and interactive problems that guide you step by step and help you build your intuition. Their courses are designed to fit seamlessly into your life, whether you are a beginner looking to build your foundation or an enthusiast diving deeper into topics like factorials, calculus, or even machine learning. Brilliant simplifies even the most complex ideas with a bite-sized interactive lessons. Recently, Brilliant enhanced their courses to make learning even more engaging, breaking down each concept into manageable bite-sized pieces. What I feel about maths is that it's never about memorizing formulas or even tricks. It's about truly understanding the concepts in a way that's gonna stick with you. One of the things that I love most is how easy it is to incorporate Brilliant into my daily routine. Whether you are tackling a lesson on your commute, taking a quick break, or winding down before bed, you will find yourself getting smarter one day at a time. So, why not explore everything that Brilliant has to offer? And you can try it for free for a full 30 days by visiting brilliant.org/warnix. You can click the link in the description or simply scan this QR code to get started. And here's the best part. If you sign up today, you'll get 20% off Brilliant's annual premium subscription. the question still remains. Why the unpredictability? Why are systems, even if they are chaotic, unpredictable? Why does the accuracy of our chaotic systems decrease over time, no matter how precise our initial conditions are? Clearly, the story doesn't end here. Even if we have all the parameters in our predicting machine and have perfectly calculated their initial values, the accuracy of our predictions will eventually decline. But why? Let's revisit the spiral chaos system. Just as the inner dots are moving far less than the outer ones, in the same way, the error in predicting a chaotic system grows over time. This error stems from inaccuracies in the calculations performed by the machine. For instance, if I query the value of angle in the console, it gives me a different value from what I am displaying in the simulation. This inaccuracy of the machine is famously known as the floating point error. Consider this perfectly invertible pendulum. In theory, if no external forces act on it besides gravity, it should remain stationary indefinitely. Yet in practice, it eventually starts moving. Because floating point errors, however small, accumulate over time, introducing slight imbalances that grow exponentially due to system's chaotic nature. And to minimize this error, the system's condition must be continuously updated. And because of the nonlinearity, the accumulation of errors makes long-term predictions increasingly uncertain. In the nonlinear dynamics, the error in calculation is determined by the Lyapunov exponent, the lambda here. The Lyapunov exponent measures how sensitive a system is to initial conditions, and it depends entirely on how the system's parameters interact and how they are handled computationally. This exponent essentially determines the time beyond which predictions become futile. For example, the parameters used to predict the tides interact in such a way that cancels out their errors, leading to a highly reliable forecast over extended periods. In contrast, the parameters governing the weather system don't behave in such a way, resulting in the error accumulation. And this is why the predictability horizon for weather forecasting is typically around 7 days or at most 2 weeks in rare cases. There is a fascinating paradox that the chaos is deterministic. In principle, the future is entirely dependent on the past, but due to the inevitable errors in the calculation, due to the nonlinearity, even the predictable behavior becomes unpredictable over time. The story of determinism of chaos is for another video. The point I'm trying to make is that no machine can eliminate uncertainty entirely, as the precise state of a system can never be fully known at any moment. In 1961, Edward Lorenz discovered this inherent limitation in the models when he accidentally observed two completely different predictions in the weather forecasting. The machine he used printed the numbers for only 3 decimal places, and as you can see, it is quite evident the difference between the two outcomes. This seemingly minor detail revealed the profound sensitivity of our chaotic systems to the initial conditions, ultimately leading Lorenz to coin the term the butterfly effect. To illustrate how the determinism of the system can give rise to chaos, he formulated a set of these equations. Now, if I arrange some points around the origin and let them evolve, we can witness the chaos as a trajectory is soon going to be evolved to be completely different from each other. Now, suppose if I arrange a million particles separated by just 0.001 units. Notice how the particles evolve over time. And after Lorenz Attractor, people started formulating new equations, giving rise to the new world of chaos. And to simulate a different model, I just need to change the differential equation here. So I tried the Isover Attractor by just changing the differential equations, and this is how it turned out.